Folks, welcome to Statistics. What's up, folks? Welcome back to the next lecture in statistics. Today we're going to be taking a look at how to compare data. To do so, we're going over to Hopkins Forest in Massachusetts. Climate scientists in the 1990s gathered data on weather, wind speed, temperature, just to understand the state of global warming and climate change. So today we're going to be examining that data and using it to understand how we can compare data. So now that we know what we're doing today, let's go ahead and write down the 5 W's: who, what, where, when, and why about our data set. Okay, so who are we collecting data about? Well, remember, who doesn't have to be a person. It could be a time period or some kind of a unit. And in this case, our who is the months of the year 1989. Months of 1989. And why is that? Well, that's simply because we're trying to find the wind speed of Hopkins Forest in Massachusetts during these months. Okay, what are we trying to do? Well, we're trying to understand the distribution of the average daily wind speed. Okay. Who, what, where? Next up is where. Where are we doing it? Well, we're conducting our data study in Hopkins Forest in Massachusetts. Hopkins Forest in Massachusetts. M-A-S-S-E-C. Okay, yeah. Massachusetts is very hard to spell, by the way. Okay. And how about when? What's our when? Well, our when is 1989, right? That's the year we're focusing on. Of course, we can't focus on more than 1 year. Well, we can. It's just going to make our data a bit crazier. And finally, why? Why are we doing this? Well, climate scientists generally examine temperature and wind speed data and these kinds of things just to get a global scale of how the climate is changing. So for why, we can write to understand climate change. Okay, so to summarize, what are the 5 W's about our data set? Well, we've got who, which is the months of 1989. We've got what, which is the average daily wind speed in miles per hour. It's always good to put some units. Miles per hour is some of the best. Where, we're conducting our study in Hopkins Forest, Massachusetts. When, 1989. And why, to understand climate change. Okay, so we've got our 5 W's about this data set. Now let's go ahead and construct the histogram that actually displays these wind speeds. Alright, folks, so we finally drew our histogram, and what do we have here? Well, first and foremost, on our x-axis we have the speed, the wind speed in miles per hour, and on the y-axis we have the number of days. Okay, so it's actually worth writing that down. I'll do that pretty soon. Now, how can we describe the distribution of our data? Well, whenever you describe data, you should remember the 5 key pillars of describing quantitative data: shape, center, spread, outliers, and context. Okay, what's the shape here? The shape here looks asymmetrical. More specifically, it looks skewed to the right because you've got this huge tail on the right. So we say from our experience that this is a right skewed histogram. Okay, that's the shape. What about the center? Well, to describe the center, we should use the median because this is a skewed histogram. When you have a skewed, use the median. When you have a symmetrical, use the mean. Okay, so the center of this distribution looks to be around perhaps this side area here, and the center also involves the fact that this is a unimodal distribution, or rather that's a shape. So we already know it's unimodal and it's right skewed. We have its shape, we have its center. How about the spread? Well, once again, because this is a skewed distribution, we're going to use the interquartile range, the IQR, instead of the standard deviation. To understand why, just watch our lecture on the mean versus median and spread. Okay, so that's unimodal, that's right skewed. How about, do we have any outliers? Well, yeah, check out this extremely windy day. That's an outlier right there, and we should investigate it. And finally, what's the context? Well, we're examining the wind speeds of the Hopkins Forest in Massachusetts for months in 1989. Okay, and of course you have your 5-number summary right here. This is your 5-number summary. Hopefully you recall that's the name. 5-number summary. And that involves your maximum, quartile 3, median, quartile 1, minimum. Now, using this 5-number summary, I'm actually going to construct something called a box plot. A box plot is another way to visualize quantitative data, kind of like a histogram. So, how do you make a box plot? Well, first and foremost, what we have to do is make a scale similar to our histogram. So our scale can kind of be a horizontal scale. You can go from 0 to 2 to 4 to 6 to 8. Now, let's put our minimum. Where's the minimum gonna be? Where's the quartile 1 gonna be? Where's the median gonna be? Where's quartile 3 gonna be? All of these are gonna be involved within the box plot. First, let's put quartile 1. Quartile 1 is at, where's quartile 1? I don't even know. 1.15. So 1.15, that's about here. That's right about here. Okay, quartile 3 is at 2.93. That's closer to 3, so I'm guessing that's about here. And the median is around 2. So we can say the median is right there. So this is quartile 1, this is my median, or quartile 2, and this is quartile 3. And you know what, I actually have space to write median. Connect these 3 guys, and this is my box. But we're not done. We got the whiskers too. Where's my whiskers gonna end up? My whiskers are gonna end up after and before. They're kind of gonna be like this and that. But we have to make it precise. Where do my whiskers go? Well, my upper fence, or my upper whisker, is gonna be quartile 3 plus 1.5 times my interquartile range. Okay, what's quartile 3? It's 2.9. And 1.5 times my interquartile range. What's my interquartile range? Well, let me go ahead and put this mic over here. What's my interquartile range? It's simply going to be the difference in my quartile 3 and quartile 1. So it's going to be quartile 3, 2.9, minus quartile 1, 1.1. So what's my upper fence going to be? It's going to be 2.9 plus 1.5 times 1.8. Okay? Now, I guess it's time to get a calculator. So, let's go ahead and calculate what this is going to be. So, calculate 1.5 times 1.8, and that's going to give us 2.7, believe it or not. And now, we're going to add that value to our quartile 3 to get 5.6. And that's going to be our upper quartile. This right here is our upper fence, 5.6. So what does that mean? Your upper fence is going to end right about here, 5.6. This is my upper fence. Upper fence. What about my lower fence? Well, I'm going to repeat the same procedure, except instead of using quartile 3 as I did for my upper fence, I'm going to be using quartile 1. So let's calculate our lower fence right here. I'm going to start with quartile 1 and subtract 1.5 times my interquartile range. So quartile 1 is what? It's going to be 1.15 minus 1.5 times my interquartile range, 2.9 minus 1.1. Okay, so what's that going to be? Well, that's going to end up being 1.15 minus 1.5 times 1.8. Okay, let's see what that comes out to be. So I'm going to end up with 1.5 times 1.8. That gives me my 2.7. 1.5 minus 2.7 gives me a good 1.55. Okay, so that's going to be my lower fence. Negative 1.55. Negative 1.55. Now you got to think, does that make sense? Can you have a negative wind speed? No. So just set your lower fence to 0. Just set it to 0. Because it doesn't make sense to have a negative wind speed, so just set your lower fence to the smallest value it can be, which is 0. And finally, don't forget your outlier, which is at 8. So go ahead and put a kind of star if your outlier is above 3 standard deviations. If it's within 3 standard deviations, you can just put a circle like that. So that right there is our outlier. And now you can kind of see what's going on, right? You can see that this is our box and whisker plot. You can see this right tail is bigger because we have a right skewed distribution. You can see that the median is at exactly half, and this is the 50%, this is the middle 50% of our data. What you cannot see is the modality. This box and whisker plot doesn't tell you if our distribution is unimodal or bimodal or whatever. So that's why the histogram is so important. So you see the best of both worlds, the histogram versus the dot plot, the box plot. So that's how you construct a box plot. Now, moving on. Alright folks, so we have all the data for spring and summer and fall and winter. Remember, this is the data for the wind speeds of the Hopkins Forest in Massachusetts for the year of 1989. We've got 4 seasons divided into 2 sets, spring and summer, fall and winter. What do we notice? Well, let me get my marker, and now we can make some noticing. So first and foremost, we see both graphs, both histograms are unimodal. But we see that they're very different in terms of symmetry. You see that the spring and summer graph is very highly right skewed, right? Because of this tail right here, we have a highly right skewed asymmetrical distribution. On the other hand, the fall and winter graphs are kind of symmetrical. They're approximately symmetrical, if you will. But we can also make further noticings, right? Because you can see the IQR. The IQR here is 1.87, whereas the IQR for spring and summer is 1.32. That tells us that there's a lot more variability going on for fall and winter than spring and summer. In other words, you don't know if you're going to walk out with an umbrella or with a kind of summer cap for fall and winter, whereas for spring and summer, there's a lot less variability. You know you're walking out with some short jeans and a summer hat. Okay, so this high IQR tells us that there's a high variability, much higher variability for fall and winter. High variability. Okay, anything else we notice? Well, the median is significantly higher for fall and winter, meaning the wind speed is significantly higher in fall and winter, as you might expect, right? So you typically get a higher typical wind speed in fall or winter. You can see the standard deviation is higher for fall and winter, telling us that the typical day will differ greater from the mean in fall and winter than in spring or summer. So if you walk out on a fall or winter day, your chance of being away from the mean is bigger than your chance of being away in spring or summer. and you look at the mean for fall and winter, clearly the mean here is pulled to the right by this extremely high outlier. Whereas for spring and summer, there's no such outliers, and most of the data is concentrated in this lower left region. Okay, so that's how you can compare these two distributions. Now let's go ahead and check out some more. Alright folks, so now I want to show you an amazing box plot. And in fact, not just one box plot, but 12 box plots, one for each of the months of 1989 that represent the wind speeds of Hopkins Forest in Massachusetts of that year. Let's check it out. Alright, so here is that amazing box plot. What are some of the things you notice? Well, I see a few things. First and foremost, I see that there's a consistent decrease in wind speed from the months of March to August. You see that? The median keeps going down and down and down and down and down. And then from August to about, just for a few more months after August, then the wind speeds keep creeping back up. Okay, that's one thing I noticed. So basically, generally the wind speeds are decreasing in summer, but increasing back up in winter. I also see that the month with the least variability is the month with the lowest IQR, or the lowest range, and you can see that very clearly in November, I think. So yeah, those are just some of the things you can notice. You can see that there's some outliers going on as well. As you can see, those outliers are represented by stars or circles above the upper fence. And yeah, that's about it. Let's go ahead and check out some more. Alright folks, so let's go ahead and compare these two box plots, these two distributions. This right here is a box plot, two box plots giving the speed of two different types of roller coasters, steel roller coasters and wood roller coasters. Alright, so what are some comparisons we can make about them? First, let's make some comparisons about the shape. Okay, remember, for shape we can say left skewed, right skewed, unimodal, bimodal, symmetric, asymmetrical. What can we say? Well, for shape I can see that steel is clearly asymmetrical because the median is not at the median doesn't cut this box in half. Okay, to put it nicely. In fact, the median is skewed. It's skewed to the right. Okay, you can see a lot of data values are scattered over a wider range, and so this tells me that, what is that? Okay, this tells me that this box plot right over here, the steel distribution is right skewed. Okay, that guy is going to be right skewed. Okay, so I've already got one in the box. Okay, one in the box. Steel is going to be right skewed because you can see my median doesn't cut the box in half. It leaves a lot of space here, meaning that I've got a lot of data values scattered over a wide range, giving me a right skewed distribution. On the other hand, you can see this median cuts the box exactly in half, so I can speculate that the wood distribution, the distribution of the speed of wooden roller coasters, is symmetrical. 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 Okay, now we're done with shape. Let's talk about the center. Okay, for center we can say things like we can use the mean and the standard deviation, or we can say we'll use the median because they're skewed. So for the center of the steel distribution, we're better off using the median because it's skewed, it's asymmetrical, it's right skewed. On the other hand, for the wooden roller coasters, we're better off using the mean as a measure of the center because it's symmetrical, right? Okay, we're done with shape, we're done with center. How about spread? Can we say anything about spread? Well, definitely we can say that the steel roller coasters have a wider range overall. Check out this huge range compared to this smaller wooden range. So they have a greater range than the wooden roller coasters. But also notice that their IQRs are approximately same. So IQRs are approximately same, but there is one thing we should know, because check it out. This over here is the 0th percentile, this is the 25th percentile, this is the 50th percentile, 75th, and 100th percentile. And of course, I forgot to draw the outlier, but there's an outlier right here. Okay? Oh, I don't have to circle it. Here's the outlier. So notice that 50% of my data values are just over here. And these 50% of steel roller coasters are faster than 75%. 75%. Okay, this right here, let me shade it in as a matter of fact. This right here is 50%. This is an additional 25%. That's 75%. And this over here is 50%. So 50% of steel roller coasters are faster than 75% of wooden roller coaster. So that's worth taking note of. 50% of steel roller coasters are faster in speed, in miles per hour, than 75% of wooden roller coasters. I think that's a very keen observation to make. Okay, that's spread. And yeah, that's steel and that's wood. Okay, shape, center, spread. Have we got anything left? Well, yes, we've got outliers left. Outliers. Okay, can we say anything about outliers? Well, there's just one outlier here that's above the upper fence, and that outlier is for the steel roller coasters. Turns out that was this right here, this roller coaster. It was not only steel, it was not only powered by the force of gravity pulling it down. So it was not only powered by gravity, it was also powered by hydraulic press, which made it extremely fast. So that explains the outlier you see above there, 120 miles per hour, powered by hydraulic press. All right, folks, that's the comparison of these two distributions. Let's check out one final distribution. All right, folks, so now we're going to check out one last standard distribution, and let's go ahead and try to compare those distributions. All right. All right, ladies and gentlemen, let's go ahead and try to compare these two data sets. What do we have going on here? Well, we have a lady and she's trying to find out how well these 4 cup holders preserve the temperature of a cup. So for example, let's say you're going to Brooklyn Tech one day and you've got some, I don't know, soup, right? And you put 4 of these cans, 4 of these lids on top of your soup, and you want to see which one best preserves the temperature, the hotness of the soup, or the hotness of the warm water you have. Okay, so which one preserves the heat or the temperature of your liquid the best? This right here, these units, 0, 5, 10, 15, 20, this represents the degree Fahrenheit change in temperature. Okay, so this could represent, for example, the whatever cup of coffee you had at home, you put on the lid and it changes temperature by 10 degrees. Okay, so it becomes cooler by 10 degrees or 15 degrees, 20 degrees. Okay, so what do we notice? Well, there's a pretty clear thing that you should notice. First and foremost, all 4 of these box plots are right skewed, right? Can you see that? You can see all of them are right skewed, and in none of them does the median cut the box in half. Okay, so all of these distributions are right skewed, number 1. Number 2, you might pretty immediately notice that Nissan is the best performer, both in cars and in terms of these coffee cup filters, because Nissan preserves the temperature the most. You can see it loses the least temperature. It has the smallest median, so Nissan has the smallest median, right? Smallest median, and of course median is the way to go when you're comparing skewed distributions like these. Nissan has the least median, but check out what else it has. Okay, you can see that this is 75% of Nissan's data, right? This is 75%. That means 75% of Nissan's cup holders preserve the temperature better than any one of these other cup filters. So that means 75% of Nissan cup filters perform better, they preserve temperature better than any one of these other alternatives. Okay, so that means Nissan is one of the best in the market, but it's also one of the most consistently performing in the market because it has a very low variability, as opposed to, for example, SIG, which has a very high variability, and you can see its median is about 14. If I come over to SIG over here, its median is 14. Look at that. That means you start with a hot cup of coffee in the morning, you go to Brooklyn Tech, by the time you're there, your coffee has cooled by 14 degrees. As opposed to if you use Nissan, your coffee would have only cooled down by 2 degrees. And so you conclude that Nissan, it has the lowest median, right? So it preserves the greatest temperature. It has the lowest variability, so it has the least change, or least risk of losing a high temperature. And so you conclude that Nissan is the best in the market. All right, folks, and that's how we compare distributions. You can also see the IQR for Nissan is the least, right? Also showing that it has the smallest range, least variability. Okay, comparing the medians, we find it also, once again, has the least overall typical change in temperature. And that's it for this lecture on comparing distributions.
Ambition plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.